Spring of 1944, Wright Field Airstrip, Dayton, Ohio. A pilot's grip tightened on the throttle control of his P-51B Mustang, pushing the lever beyond the typical combat power limits. The Packard Merlin engine thundered as manifold pressure climbed toward 75 inches, drawing power from an untested aviation gasoline known only by its designation, 150 grade. The airspeed needle swept past figures that marked the boundaries of Allied fighter performance. At an altitude of 25,000 feet, the fighter was accelerating beyond 448 miles per hour. Ground-based engineers watched with intense focus as static crackled through the radio with the pilot's voice. This represented more than incremental progress. They were witnessing a transformation contained within purple-colored aviation fuel, a chemical breakthrough so significant it would invalidate every calculation the German Luftwaffe had made about American fighter performance. The European air war stood on the brink of transformation, and the driving force wasn't a revolutionary aircraft platform or innovative combat tactics, but rather a fuel formulation that enabled existing fighters to operate at levels the enemy thought impossible. German military planners remained unaware that Allied petroleum scientists had accomplished something the Reich's coal-based synthetic fuel industry could never replicate. While Luftwaffe aircraft struggled with B-4 fuel rated at 91 octane on lean settings, and their premium C3 formulation barely matched Allied 130-grade performance, American refineries were manufacturing aviation gasoline with a performance rating of 150. The ramifications were extraordinary. A Mustang powered by conventional 130-grade fuel achieved 437 mph at 25,000 feet. That identical aircraft, with the same pilot at the same height, using 150-grade fuel, could surpass 448 mph. Luftwaffe pilots who had developed healthy respect for the Mustang's operational range and high-altitude capabilities were about to learn that American engineers had rewritten the rules of air combat. The Messerschmitt Bf-109G, Germany's primary fighter in early 1944, topped out at 400 mph at altitude. The Focke-Wulf 190A could achieve 408 mph under ideal circumstances. Against Mustangs burning 130-grade fuel, German aviators could at least attempt favorable engagement scenarios. Against Mustangs burning 150-grade fuel, Luftwaffe fighters operated under a performance deficit that neither pilot expertise nor tactical brilliance could compensate for. This advantage originated not from wartime necessity, but from peacetime research by petroleum engineers who recognized that octane measurements indicated how much an air-fuel mixture could withstand compression before uncontrolled ignition. Greater compression ratios produced more power per combustion event. Additional power translated to faster aircraft and improved operational altitudes. The underlying science was simple, but producing high-octane aviation fuel on an industrial scale demanded extraordinary engineering sophistication. By 1940, as European warfare intensified, American aviation fuel manufacturing focused on 87-octane gasoline. This proved acceptable for civilian aircraft and initial military trainers, but completely inadequate for high-performance combat planes. The British, desperately seeking any edge against numerically superior Luftwaffe forces, collaborated with American petroleum companies to create 100-octane fuel, which arrived just as the Battle of Britain commenced. The impact was immediate and dramatic. British Spitfires and Hurricanes utilizing 100-octane fuel suddenly gained 30 to 40 mph in additional speed at altitude, with climb performance increasing between 500 and 1,000 feet per minute. German pilots who had enjoyed performance superiority with their 91 to 100-octane fuel abruptly found themselves on equal footing. The creation of 130-grade fuel represented another quantum leap. This formulation, carrying a performance number of 130 on rich mixture configurations, became the foundation of Allied aerial dominance throughout 1943. It energized Merlin engines in Spitfires and Mustangs, Allison power plants in P-38 Lightnings, and the enormous Pratt & Whitney R-2800 radials driving P-47 Thunderbolts. Manufacturing capacity expanded rapidly under the leadership of aviation fuel pioneer General James Doolittle, who had campaigned throughout the 1930s, convincing military leadership and petroleum corporations to fund high-octane fuel research. By 1943, 17 Allied refineries were manufacturing high-octane aviation gasoline using the catalytic cracking technique perfected by French émigré engineer Eugene Houdry. American facilities alone generated millions of gallons monthly, sufficient to sustain the massive bombing campaign against Germany and the expanding fighter forces protecting those bomber streams. German fuel manufacturing, conversely, remained constrained by dependence on coal-derived synthetic fuel. The complex process converting German coal into aviation gasoline was technically viable but sluggish and resource-demanding. Even at maximum output, Germany could manufacture only a fraction of the high-octane fuel streaming from American refineries. Most Luftwaffe fighters operated on B-4 fuel rated approximately 91 octane on lean mixture settings. Their premium C3 fuel, employed primarily in BMW 801-powered Focke-Wulf 190s and selected Messerschmitt variants, roughly equaled Allied 130-grade performance, but existed in severely limited quantities. Comprehending fuel performance requires understanding a core principle of internal combustion. Octane ratings measure resistance to detonation. When a piston compresses the air-fuel mixture during compression stroke, temperature and pressure rise dramatically. If fuel ignites spontaneously before spark plug activation, the result is detonation, an uncontrolled explosion rather than controlled combustion. Detonation generates shock waves that damage or obliterate engine components. Higher octane ratings indicate fuel can withstand greater compression without detonating. Octane ratings cannot exceed 100 by definition because 100 octane represents detonation resistance equivalent to pure iso-octane, the reference benchmark. Performance numbers quantify how much superior to pure iso-octane a fuel performs. Fuel with a performance number of 150 can withstand 50% more compression than pure iso-octane before detonating. Manufacturing such fuel demanded adding anti-knock compounds, predominantly tetraethyl lead, and precise blending of aromatic hydrocarbons like toluene and xylene with base gasoline. British fuel scientists at the Royal Aircraft Establishment tested countless blends through 1942 and 1943, pursuing the optimal balance of anti-knock performance, energy density, and production feasibility. American researchers at Wright Field conducted parallel studies, exchanging information with British colleagues. By early 1943, both nations had manufactured experimental quantities of what they designated 150-grade fuel. The nomenclature was somewhat deceptive because it suggested an octane rating of 150, which was chemically unattainable. What it actually signified was fuel with a performance number of 150 on rich mixture settings combined with 100 octane performance on lean mixture settings. This formulation, dyed purple for immediate identification, underwent comprehensive evaluation through 1943. The outcomes exceeded projections. Merlin engines operating on a 150-grade fuel could maintain manifold pressure readings of 75 inches of mercury compared to 67 inches on 130-grade fuel. This converted directly into increased horsepower. A Packard Merlin V-1657, the power plant propelling the P-51D Mustang, generated 1,490 horsepower at standard military power on 130-grade fuel. The same engine operating on 150-grade fuel at war emergency power settings produced approximately 1,720 horsepower in the P-51B with its V-1650-3 Merlin variant. Flight evaluation at Wright Field confirmed that performance improvements were substantial across all flight conditions. Maximum velocity increased by approximately 25 to 30 mph at altitude. Climb rate improved by several hundred feet per minute. Most significantly, these enhancements required no aircraft modifications whatsoever. The identical Mustang flown one day on 130-grade fuel, and the following day on 150-grade fuel became measurably faster and more capable solely because of what flowed through its fuel system. The determination to introduce 150-grade fuel to operational fighter squadrons came in early 1944. The timing reflected careful deliberation. The 8th Air Force, stationed in England conducting daylight strategic bombing missions deep into German territory, was experiencing unsustainable attrition. Despite the arrival of initial P-51 Mustangs in December 1943, Luftwaffe fighters continued inflicting devastating casualties on American bomber formations. American planners required not merely a long-range escort fighter, but an escort so fast that German interceptors couldn't easily disengage or decline combat on disadvantageous terms. In May 1944, initial operational shipments of 150-grade fuel reached England. Distribution was strictly regulated. Not every fighter group received the new formulation immediately. The 8th Air Force began with selected squadrons both to manage supply coordination and to assess combat effectiveness. The British Royal Air Force, which had spearheaded much early testing, also began equipping fighter units with the new fuel. Priority went to squadrons assigned high-speed interception duties, particularly those hunting German V-1 flying bombs that began terrorizing London in June 1944. The V-1 cruised at approximately $400 mph at low altitude. Intercepting these weapons demanded fighter aircraft capable of matching or exceeding that velocity at sea level or low altitude, where atmospheric density reduced all aircraft performance. Hawker Tempests and Spitfire P-51s could barely overtake the V-1s. Mustangs burning standard fuel were marginal. Mustangs burning 150-grade fuel possessed sufficient speed margin for reliable interception. On June 18, 1944, Major R.E. Turner of the 356th Fighter Squadron destroyed a V-1 flying bomb by tipping its wing with his P-51's wingtip, demonstrating a technique employed at least 16 times during the campaign. This maneuver demanded exceptional velocity and precision to position the fighter's wingtip within 6 inches of the V-1's wing surface, then exploit the airflow to roll the flying bomb off course and send it plummeting. The first extensive combat employment of 150-grade fuel by American P-51 pilots occurred in June 1944, coinciding with the Normandy invasion. Fighter groups of the 8th Air Force, assigned to achieve air superiority over invasion beaches, flew combat air patrols and bomber escorts using the new fuel. German fighter pilots began reporting encounters with Mustangs that performed beyond their previous experience. Luftwaffe intelligence officers compiled pilot reports describing American fighters that couldn't be overtaken in any flight regime, that could accelerate away from German interceptors effortlessly, and that seemed to possess power reserves that defied explanation. These reports were initially dismissed as pilot error or exaggeration. German fighter pilots, intelligence officers reasoned, were exhausted, outnumbered, and facing mounting casualties. Their accounts of superior American fighter performance were surely products of stress and fatigue rather than actual performance increases. This assessment was fundamentally incorrect, though the truth wouldn't become apparent until after hostilities ended. Gerhard Barkhorn, a Luftwaffe ace with 301 victories primarily achieved on the Eastern Front, flew combat missions against American fighters over Germany in 1944. After the war, in interviews conducted during the 1970s and 1980s, he discussed his encounters with late-war Mustangs. He recalled being astonished at the performance of American fighters during the conflict's final year. Barkhorn, who subsequently test flew captured American fighters including the P-51, P-47, and P-38, noted that the Mustang particularly impressed him with its velocity, climb capability, and high-altitude performance. What Barkhorn and other German pilots didn't realize during combat was that they faced an aircraft whose performance had been chemically enhanced beyond its designed specifications. Operating at power settings the original Mustang engineers had never contemplated, the Merlin engine designed by Rolls-Royce and manufactured under license by Packard had been engineered with careful attention to thermal boundaries, bearing loads, and detonation margins. Operating an engine at higher boost pressures pushed all these parameters closer to their limits. What made 150-grade fuel revolutionary was that it permitted engines to operate at these extreme settings without the catastrophic detonation that would have destroyed engines burning lower-grade fuels at identical boost pressures. The chemistry underlying this capability involved complex interaction of fuel molecules, air molecules, heat, and pressure inside the engine's combustion chamber. Tetraethyl lead, the primary anti-knock additive, functioned by disrupting the chemical chain reactions leading to spontaneous ignition. But trade-offs existed. Tetraethyl lead was highly toxic, requiring careful handling by ground personnel. It deposited residue on spark plugs, valves, and cylinder walls, increasing maintenance demands. 150-grade fuel, with its exceptionally high lead content, accelerated these maintenance challenges. Fighter groups utilizing the new fuel experienced more frequent spark plug fouling and increased cylinder wear. American maintenance protocols adapted swiftly. Spark plug replacement intervals were reduced. Cylinder inspections became more frequent. Engine overhaul schedules were adjusted. The performance gains were judged worth the increased maintenance burden. For pilots, the transition to 150-grade fuel demanded new operating procedures. Manifold pressure limits were elevated. Pilots had to avoid overboosting engines, particularly at low altitudes where air density was greatest. Most significantly, pilots had to learn fuel consumption management. 150-grade fuel provided more power, but operating at maximum boost consumed fuel rapidly. Escort missions to Berlin and back already pushed the Mustang's range to its boundaries. Utilizing the new fuel's full capability meant careful fuel management, understanding when to employ maximum power and when to throttle back for cruise efficiency. Combat reports from summer and autumn 1944 document the transformation. 8th Air Force fighter groups equipped with the new fuel reported higher victory-to-loss ratios and increased ability to intercept German fighters attempting to attack bomber formations. German fighters that had previously been able to execute fast slashing attacks and then escape now found themselves unable to outrun pursuing Mustangs. On August 6, 1944, during Operation Frantic missions to Soviet air bases, Lieutenant Urban Ben Drew of the 361st Fighter Group engaged German fighters over Eastern Europe. Flying his P-51D and utilizing 150-grade fuel, Drew demonstrated the speed advantage this fuel provided. The performance margin proved decisive in numerous engagements throughout this period. The psychological impact on Luftwaffe pilots was substantial. Already outnumbered and confronting superior Allied numbers, they now faced American fighters that appeared to possess unlimited performance margins. Their tactical options contracted dramatically. They could attempt mass attacks, hoping sheer numbers would overwhelm the escorts. They could refuse combat entirely, preserving their aircraft and pilots. Or they could engage and likely be shot down by Mustangs that were faster, more maneuverable, and flown by American pilots who were growing increasingly confident and aggressive. Reichsmarschall Hermann Göring, Luftwaffe commander, famously remarked upon observing P-51 Mustangs over Berlin that he knew the war was lost. This comment reflected the Luftwaffe's strategic predicament. The Mustang's extended range meant nowhere in Germany was secure from American daylight bombing. The introduction of superior fuel in mid-1944 intensified this crisis. Luftwaffe technical intelligence eventually obtained samples of Allied 150-grade fuel from captured drop tanks or crashed aircraft. German fuel chemists analyzed the samples and confirmed what Luftwaffe pilots had been reporting. The Americans had developed aviation gasoline with performance characteristics exceeding anything German synthetic fuel plants could manufacture. Allied bombing of German synthetic fuel facilities, particularly the raids on Luna and other major installations in May and June 1944, further constrained German fuel production. By late 1944, the Luftwaffe was rationing fuel. Fighter units received priority, but even they operated under severe constraints. Training for new pilots was drastically reduced. Many German pilots reached operational units with minimal flying experience compared to American pilots, who typically accumulated several hundred training hours before entering combat. Between January and May 1944, before widespread introduction of 150-grade fuel, American bombers suffered loss rates of approximately 3 to 6% per mission. These were sustainable but painful casualties. Between June and December 1944, after the introduction of 150-grade fuel and achievement of air superiority, loss rates dropped below 2% per mission. Fighter victories increased dramatically. American P-51 groups across the 8th, 9th, and 15th Air Forces claimed approximately 4,150 German aircraft destroyed in air-to-air combat between late 1943 and May 1945, with a significant portion of those victories occurring after June 1944. The German pilot force, which had entered 1944 with substantial experience despite heavy Eastern Front losses, was systematically eliminated. The technical specifications of 150-grade fuel merit examination. The fuel's lean mixture octane rating of 100 meant it resisted detonation as effectively as pure iso-octane when engines operated at cruising power settings. The fuel's rich mixture performance number of 150 meant it could withstand 50% more compression than iso-octane when engines operated at maximum power. This combination allowed pilots to cruise efficiently for maximum range, then switch to rich mixtures at high power for combat, confident the engine wouldn't detonate even at extreme boost pressures. Handling procedures for 150-grade fuel required special precautions due to high tetraethyl lead content. Ground crews wore protective equipment when refueling aircraft. Spills were cleaned immediately to prevent lead poisoning. Fuel trucks and storage tanks were clearly marked to prevent accidental mixing of fuel grades. Despite these precautions, the safety record was excellent. Industrial accidents were rare. The transition in operational squadrons required pilot training. Pilots received briefings on the new fuel's properties and updated engine operating procedures. Manifold pressure limits were raised. Operational guidelines specified when and how to use maximum power settings. Aircraft required no modifications. The engines, fuel systems, and all components were compatible with both grades. This compatibility simplified logistics and operations. The production statistics tell a story of industrial mobilization on a scale Germany couldn't match. Between May 1944 and April 1945, the 8th Air Force consumed over 53 million gallons of 150-grade fuel. Allied production across all refineries likely exceeded 200 million gallons during operational use. Each gallon required refining infrastructure, chemical additives including toxic tetraethyl lead, quality control testing, transportation to Europe, storage in secure facilities, and distribution to dozens of airfields. American industrial capacity in 1944 operated at levels that seemed almost miraculous. Factories produced bombers by the thousands and fighters by the tens of thousands. Shipyards launched Liberty ships faster than Germany could sink them. Oil refineries produced aviation gasoline in quantities exceeding Germany's total fuel production across all grades. The Royal Air Force used 150-grade fuel extensively in fighter operations over Europe. British squadrons flying Spitfire 14s, Tempest 4s, and Mustang the 3s and IVs received priority allocation of the new fuel. RAF pilots reported similar performance improvements to those experienced by American pilots. The Tempest, already among the fastest piston-engine fighters in service, became even more formidable. Tempest squadrons achieved remarkable success against V-1 flying bombs. Between June and September 1944, RAF 150 Wing Tempests shot down 638 flying bombs, with No. 3 Squadron alone claiming 305. Squadron leader Joseph Berry destroyed 59 V-1s, and the performance margin proved valuable in every role. The combat effectiveness of 150-grade fuel was proven repeatedly through late 1944 and early 1945. Fighter groups that received the new fuel reported increased victory claims and reduced losses. By March 1945, virtually every P-51 unit was operating on the fuel. Combat reports from this period show overwhelmingly one-sided results. German fighters rarely challenged Allied formations effectively. When they did engage, they usually suffered devastating losses. In April 1945, missions over Germany often encountered no aerial opposition. The Luftwaffe was finished, destroyed by attrition, fuel shortages, and the systematic elimination of experienced pilots who couldn't be replaced. On May 8, 1945, Germany surrendered. The air war over Europe ended with absolute Allied air supremacy. This supremacy had multiple causes. The P-51 Mustang's extended range was crucial. American pilot training was excellent. Allied numerical superiority was overwhelming. But the petroleum engineering advantage that 150-grade fuel provided was significant. The purple-dyed gasoline transformed good fighters into exceptional fighters, gave Allied pilots confidence, and represented the accumulated technological and industrial might of nations that could outproduce, out-innovate, and ultimately outlast their opponents. Velocity matters in aerial combat. A faster fighter can choose when to engage and when to withdraw. A faster fighter possesses tactical flexibility that slower opponents lack. When American fighters became demonstrably faster through the combination of excellent airframe design and superior fuel, the Luftwaffe's tactical options narrowed dramatically. The contrast between German and Allied situations in late 1944 and early 1945 was stark. Allied fighters could fly multiple combat missions daily, limited only by pilot fatigue and aircraft maintenance. German fighters often sat grounded for lack of fuel. When they did fly, they operated under strict fuel conservation measures that limited combat capability. This operational flexibility had strategic implications. Allied fighters could maintain standing patrols, react to threats aggressively, and sustain operations continuously. German fighters had to choose their moments carefully, conserve fuel rigidly, and often break off combat, not because they were losing, but because they were running low on fuel. The story of 150-grade fuel is a story about industrial warfare. Victory belonged to the side that could produce not just more aircraft, but better performing aircraft. Not just adequate fuel, but superior fuel. Not just sufficient trained pilots, but an overwhelming surplus of well-trained pilots backed by an industrial base that could replace losses faster than the enemy could inflict them. American and British fuel chemists working in laboratories and refineries never flew combat missions over Germany. They never faced anti-aircraft fire or enemy fighters, but their work, measured in performance numbers and manifold pressure readings, helped decide who controlled the skies over Europe in 1944 and 1945. Every time a P-51 pilot advanced his throttle and felt his Mustang surge forward with power that German fighters couldn't match, he benefited from chemical engineering that transformed crude oil into a fuel that made the exceptional routine. German planners had assumed American fighters would perform within predictable parameters based on aircraft design and standard fuel capabilities. What they encountered instead were fighters whose performance exceeded their calculations, sustained by a fuel production infrastructure so vast and sophisticated that it represented industrial capacity Germany couldn't counter. By spring 1945, as Allied armies overran Germany from east and west, the Luftwaffe had effectively ceased to exist as a coherent fighting force. A few units still flew, often with barely enough fuel for a single sortie. Jet fighters like the Me-262 represented a technological leap forward, but they arrived too late and in too few numbers, handicapped by fuel shortages and the absence of experienced pilots who had been systematically destroyed in combat. 150-grade fuel wasn't solely responsible for this outcome, but it was a significant contributing factor. It represented the margin of superiority that made the difference between a close fight and a decisive victory. The 448 mph that a properly boosted P-51 could achieve represented not just velocity, but also technological superiority and industrial capacity. This is what German planners hadn't anticipated, that American fuel chemists and petroleum engineers, working far from any battlefield, could create a weapon as effective as any gun or bomb. That purple-dyed gasoline could influence aerial combat as surely as superior tactics or better training. The P-51 Mustangs that flew over Berlin in early 1944 were remarkable aircraft. The P-51 Mustangs that flew over Berlin in early 1945 were the same aircraft, but they were powered by fuel that made them faster, more powerful, and more effective. That difference, measured in octane numbers and performance ratings, in manifold pressure readings and airspeed indicators, was one of many differences that decided who would win the war for Europe's skies. In that decision lay the fate of Nazi Germany and the demonstration of Allied industrial might, expressed as a purple liquid pumped into fuel tanks, burned in powerful engines, and transformed into victory one combat mission at a time.